Welcome. The topic we'll be discussing in this session is synchronization hardware. That is, how process synchronization can be achieved through hardware. Okay. So through hardware support also, the process synchronization can be achieved. That is, the critical section code can be executed in a synchronized way, and we can ensure that there is no data inconsistency. So basically, this is done by using the concept called lock. So lock in the sense, before entering to a critical section, the particular process will check whether it is already locked or not. Whether it is already locked or not. So we'll be maintaining a shared variable. The processes will maintain a shared variable called lock, which will be accessible by all the processes which want to access the critical section. So before accessing a critical section, the particular process will check whether lock is true or not. If lock is true, means somebody is already in the critical section, so it is locked. Then this current process will wait. It will wait until lock becomes false. The moment lock becomes false, this process will enter the critical section and it will get the things done. So basically, this is the concept by which it works. So the main idea of process synchronization is, when one process is in the critical section, no other process should be in the critical section. Okay. So this can be easily achieved in uniprocessor system by disabling the interrupt. Okay, say process P1 want to enter the critical section. Okay, so it checks locks, and if lock is false, it is going to enter. But checking lock alone will not do the things, because, okay, if by checking lock, it ensures that other concurrent processes will not enter into the critical section. Okay, that is ensured. But sometimes an interrupt may access the critical section. Sometimes an interrupt may access the critical section. So in uniprocessor system, that can be avoided by disabling the interrupt. That is, when a process enters into a critical section, first it will disable the interrupt and then it will enter the critical section. And similarly, when it is coming out of critical section, it will disable the interrupt. Okay. So this can be effectively done by disabling the interrupts in a uniprocessor system. But coming to a multiprocessor system, this cannot be done efficiently. The reason is, to disable the interrupt in a multiprocessor system, first of all, when you execute a interrupt disable command, the signal should reach all the processes. So it will take considerable amount of time. And processor, in every processor there will be a clock. The clock also updates based on interrupts. So if you stop the process, if you stop the interrupts, then the processor clock also may stop. So hence disabling interrupts in a multiprocessor system is not an efficient solution. Okay, so in that context, the hardware based solutions are available to ensure that process synchronization can be achieved effectively. Okay, so we will be in this particular topic, especially we will be discussing some hardware based solutions which are used to solve the problem of critical section and to ensure process synchronization. Okay, so these hardware solutions are based on atomic instructions. These hardware solutions are based on atomic hardware instructions. So what is meant by an atomic hardware instructions? Atomic hardware instruction means two or more instructions will be executed something like a single instruction. Okay, actually it may be, the hardware may be executing two or more instructions, but these two or more instructions will be treated as a single instruction and then it will be executed. So that is called as atomic instruction. That is, when this set of instructions is executed, nothing can be interrupted, no interrupts will be allowed. So only this, all these interrupts will be executed as one entity or one bunch. So that feature is called as atomic hardware instructions. So atomic means it will be executed as one single unit and they will be non-interruptible. So we will be discussing such two examples for hardware based synchronization. One is called as test and set instruction. One is called as test and set instruction. The other one is called as compare and swap instruction. So this is the agenda of this topic. So basically we'll be discussing two types of hardware synchronization instructions. One is test and set instructions and the other one is compare and swap instruction. Okay. So before that, let us try to understand how the concept of key works. How the using the how the concept of lock works. Using the concept of lock, how synchronization is achieved. So if a process want to access the critical section, first, first it should try to acquire the lock. First it should try to acquire the lock. So during this process of acquiring the lock, the process, what it will do in the sense, it will check the shared variable lock, what it contains, whether lock is true or false, or 1 or 0. If lock is equal to true, if lock is equal to true, then it means that somebody else is using the lock. If the current value of lock is true means, then it means that somebody else is in the critical section. So the critical section is already locked, is already locked. So this particular process, if this process is PI, then PI will first check what is the value of lock. If lock is true, then PI, the process PI will understand that somebody else is in the critical section, so it will keep on wait. It will not enter into the critical section. It will keep on wait and it will keep on check whether lock is becoming false or not. At one point of time, lock becomes false. If lock is false, then it means that currently nobody is in the critical section. If lock is false, it means that currently nobody else is in the critical section. Okay. Then this particular process PI will enter into the critical section. The moment it enters into the critical section, it will make lock equal to true because somebody else should not enter. Okay. So the moment it enters into critical section, it will make lock equal to true, and then it will start executing the code corresponding to the critical section, and then it will release the lock. Releasing in the sense, it will just make lock equal to false. So again, if lock is made as false, it means that if some other processes are waiting to enter the critical section, they can enter into the critical section. Okay. So once it makes lock, once it made lock as false, then it will execute the remainder section. Okay. So this is how uh, the process synchronization can be ensured by using lock concept. Okay, but so here this is what is entry section, and this is the actual critical section, and this is the exit section. Okay. So now we'll be discussing two hardware based solution, but this solution is, so here we should also disable the interrupt. Disabling the interrupt is okay with uniprocessor system, but it is not okay with multiprocessor system because it may lead to other overheads. Okay. So we are looking for some other solution. So in that context we are discussing this topic, hardware based synchronization. So we'll be discussing two such hardware based synchronization example. One is test and set instruction, the other one is compare and swap instruction. So first let us discuss about test and set instruction. So this is how the test and set instruction is given in the hardware. Even though this instruction, this function, even though this function contains three statements, but all these three statements will be executed as a single statement. It will be executed as a single unit. Okay, so that is called as atomic execution. So they will be executed as one single unit, which is called as atomic execution. Okay, so let us try to understand what this particular code is doing. Okay, what this particular code is doing. So this particular function, it is taking one boolean variable which is a pointer variable, and it is target. Okay, so this target, so you know about pointers, right? So pointer, so with pointer we use two types of symbols. One is star. Star represents value at, star represents value at so and so location. Star represents value at so and so location, and the other one is ampersand. Ampersand represents address of. Ampersand means address of that particular location. So that is what ampersand means. Okay. So here So star can be used to represent two things. One is for declaring pointer also we use star. Otherwise also we use star to represent value at. If star is used in the right side, then it is called as value at. If it is used in the declaration, then it means you are declaring a pointer. Here you are using star. It means you are declaring a pointer called target, which is of type boolean. Okay. Again here we are creating a normal boolean variable RV, some random variable, which is equal to star target. So whatever the value, so target is some variable which can hold a boolean value, Okay. So that is this target can hold either true or false. We don't know what it is currently. It depends. It can hold either true or false, not any other value. Okay. So RV is equal to star target means whatever is in target that is stored in RV. If true is in target, then true will be stored in RV. Okay, because star represents value at. Star represents value at. So this star here you should read it as value at target. Okay, it is not address, value at target. So what is the value at target? It can be either true or false. If it is true, true will be moved to RV. If it is false, false will be moved to RV. And then we are just making star target equal to true. Again here star target means value at target equal to true. So value at target now you are changing to true. Value at target now you are changing to true. Previously it may be either true or false. Now we are making it true. And then we are returning true. Sorry, we are returning RV. We are returning RV. So RV is the original value of target. It may be either false or true. That value we are returning. So this is what this function does. And if at all this function is called, then the hardware will ensure that this all these three statements will be executed at a stretch. That is this is an atomic instruction. Okay. So this is executed atomically. It returns the original value of the paused parameter, whatever the value of target that is, it returns. It sets the new value of the paused parameter to true. Always it sets the new value of the target to true. Okay. Now how this function can be used. So this is how this function is defined, how it can be used. Let us see with an example. So let us assume there is a shared variable lock, which is shared between multiple processes which want to ensure synchronization, and initially this variable is assigned to false. Initially it is assigned to false. Okay. So here is an example. So this particular code, what it does in the sense, this is an infinite do while loop, then while test and set of lock. So here address of lock is paused. Okay, while test and set of lock. Okay, so pointer needs an address, right? Pointer needs an address. So there is a shared variable lock. There is a shared variable lock. Okay, so as the question says, it is initialized with false, or initially it is false as it is given there. So it is false. Let us assume it is false. Okay, initially it is false. Over execution, it may become false or true or whatever it may be. Now this address you are passing to this function test and set, which is atomic function. That is, it will execute as one single unit. Okay, this, let us say this address is 2000. This address is 2000. This 2000 address is passed to test and set function. Okay, so this is the test and set function. So now it got the address 2000. So that is, target is a pointer. Target is a pointer. Okay, target is a pointer. Basically target is a pointer and it is pointing to an address. And what is that address? That address is 2000. That address is 2000. Okay, and that address contains a value. What it contains? False. Okay, that is what we have seen in the previous slide. So that address contains the value false. Okay, now that function, it calls this particular test and set, and it is sending the target thing. So now what we are doing, RV is equal to star target. So this star target means what? Value at target. Value at target is what? False. So what will be RV? RV also will be false. RV will be false in this case. Okay. Then what we are doing, star target equal to true. What is star target? Star means value at. Value at target, you are making it to true. Previously it is false. Now you are changing it to true. Now you are changing it to true. Okay, so previously it is false, now we are making it to true. Okay, then what we are doing, then we are returning rv. Returning rv is false, so it means false is returned. False is returned. Okay, so this function, it so so basically while test and set, what it returns in the sense here false is returned. Okay, if false is returned, this while loop will break. This while loop will break. That is, this while loop will keep on spin as long as it is true. See, this is an infinite loop without any instruction. This semicolon you can put here also or here, no problem. Okay, so this is basically, there is no instructions inside the while loop. It just calls the test and set with the lock value and checks what it returns. If it is true, as long as it is true, it will keep on spinning here. As it is false, this while will break. So the while breaks. So if it is false, it means lock is false. If it is false, it means nobody is currently in the critical section. That is, it means it is not locked. So it means this particular process, if this is process pi, it means this particular process can enter into the critical section. So it enters the critical section, it executes the critical section. After finishing the critical section, it makes lock equal to false and then it executes the remainder section. Okay, so this is the case if lock is false. Okay, if lock is false means that nobody is previously execute in the critical section. So this particular process is able to enter. Let us see the case what will happen if lock is true. So let us assume initially lock is not false. Let us assume initially lock is not false, but lock is true. So now this process pi checks. Now this process pi calls this test and set instruction, which is an atomic instruction, which will be executed in one single stretch without any context switch in between. So now the lock value is true. So the same address, let us assume. Okay, so that is now passed here. Okay, now target contains true, it is not false. Target contains true. Okay, so here we are doing rv is equal to star target. Now what is target? Target is not false, star target is value at target. Now the value at target is true, so now rv will be set as true. Now rv will be set as true, and then what we are doing, star target is equal to true. Already it is true, again we are making it to true. Fine, once again we are making it to true, and then return rv. What is rv? Rv value is true, so now true is returned. So true is now returned. So now when it comes here, what it returns here in the sense, what test and set function, the atomic function returns in the sense, it returns true. It returns true. It means that somebody else is already using the critical section. So this particular process pi cannot now enter into the critical section. So as this while loop returns true, again it will call test and set with lock value. So like that it will keep on checking. So this is called a spin lock. It will keep on rotating here. Okay, so maybe some other process pj is using the critical section. Okay, so when that process pj finished executing the critical section, obviously after the critical section the statement is lock equal to false. So at that time lock becomes false. So because it is a shared variable, it is not only for pj also using the same variable. So when it make lock as false, this will become false, then pi will be able to enter. Okay, so this is how this test and set instruction ensures that uh, uh, two process can be synchronized effectively, and also it ensures that the data consistency can be maintained. Okay, so let us stop here. We will be discussing about compare and swap instruction in the next lecture. Thank you.